My name is Helen He from NERSC. Welcome everyone to join today's CUDA training session number 5. Our usual organizer and host, Tom Papaziodor, is occupied at a GPU hackathon. He's not here today. On the NERSC side, we also have Kevin Gott, and also speakers and presenters and helpers from NVIDIA, the great team. Bob Cravella and Robbie Sears and Max Katz online. And so thanks for just everything becoming on remote, and for the speakers and the attendees to be still able to join us and organize this event, keep this ongoing. So just a reminder, people, the NERSC site, if you want to follow any exercises, we do have a reservation called CUDA training. I'll put some commands in the chat room so you can follow. Otherwise, let's start with Bob's usual excellent presentation on atomics, reduction, and warp shuffle.
Thanks, Helen. Do you have the recording started?
Yes.
Okay, good, thanks. Welcome everyone, my name is Bob Cravella. I'm a solution architect at NVIDIA. I'm joined by a couple of my colleagues, Max and Robbie, who Helen has already introduced. And this month, this is our 5th installment of a CUDA training series. I want to thank the various folks at Oak Ridge and NERSC and Berkeley Lab, Helen and Tom and others who have facilitated this and made this possible. And today we're going to be covering a topic called atomics, reductions, and warp shuffle. This, in my mind, is a little bit of a departure. In the past 4 sessions, my opinion is that that is what I would call foundational material. If anyone was wanting to do some serious CUDA development effort, I would want them to have at least that level of training, those several hours, let's say, of training under their belt before they embarked on some serious CUDA development work. What we're going to be doing for the remaining 5 sessions in this series over the next, roughly speaking, 5 months will be to look at specific topical areas. I'm calling this material now no longer foundational. Obviously, that's a matter of judgment. After you get to the end of this session today, for example, you might consider this to be fairly foundational material. But nevertheless, we're going through a transition now from what I would call foundational material in the first 4 or 5 sessions to what I'm going to refer to as topical material over the remaining 4 or 5 sessions. So this month, we're going to be looking at atomics, reductions, and warp shuffle. Those sound maybe like 3 different topics, but actually, as we'll see, there's a lot of interrelation between those topics, and they can all be used actually to solve the same kinds of programming problems, and so that is our motivation. This is a little bit more detail of what we're going to be covering today. One of the things that I'd like to point out also from a procedural standpoint is that we're choosing to work a little bit differently today, and I'll try and explain that. We're going to have roughly the same format for the session, the online session that we have today for you. So roughly speaking, the first hour will be presentation material, and the second hour will be available for questions and answers, and in particular, any questions that there may be about the homework. However, if you've perhaps taken a look at the homework, you may have noticed that it's a little bit more involved than the previous homework sessions. And so there's more activity in the homework, and there may be more areas where questions may arise as you're working on the homework. So in light of this, what we decided to do on the NVIDIA side is we decided to offer a special additional session. The idea is that we'd like to not spend a lot of time going through the homework in detail today. Instead, based on the material that you learned today or received today, what we'd like to do is give you the opportunity to do the homework on your own. And then what we'd like to do is have a special additional session that would cover the homework in much more detail than what we plan to do today. We're certainly available for questions. Any questions that you may have, we'll try to address those today. But we want to have an organized session where we go through the homework in some level of detail. Just from a logistics standpoint, what I'd like to do is point out where that is. So if you go to, I think I'm probably, okay, Helen has actually put it in the chat window. If you go to the resource page that Oak Ridge hosts for this event, you'll find a new tab that details or has the details for this additional Module 5 exercise walkthrough that is to the right of the tabs where you would find, for example, the homework and the presentations. So there's an additional new tab on this page, and the new tab has the information that Helen has placed already in the chat. So I just want to point out that we have a little bit of a different structure for what we're going to try and do today. Just be aware of that. It'll become more evident when we get to the end of the presentation material. I'll turn it over to Robbie at that point. Okay, so let's dive in. The first thing that we're going to do is atomics. We're going to talk about what atomics are and why they might be interesting and useful. In order to set that up, I would like to give you a motivating example. And this is, I believe, an important area to spend some time thinking about and talking about. If you look at most of the work and most of the homework assignments we've done so far in this series, they fall into a particular category of problems that I'm going to be discussing on the next slide. I'm going to refer to those problems typically as transformations, and as we'll see on the next slide, transformations have a characteristic from an algorithm standpoint where they take a data set of a particular size and, generally speaking, produce a data set of approximately the same size as the output. The output data set size is comparable to the input data set size. However, let's take a look at the code that I have depicted here. This is just C code. This isn't CUDA code at this point. But I have an array, or yeah, let's call it an array called A of size 100,000. And what I'd like to do fundamentally is get the sum of all the elements in that array. So I initialize that array of length size with particular set of values. And then I have a variable where I'm going to capture the running sum, and I'm calling that variable sum, and I'm initializing it to 0. And then I'm using a for loop to iterate over the elements of the array A and add each element to the running sum. This would be a very straightforward, very obvious way for a typical C programmer to realize a piece of code that would provide the running sum of that array, or the entire sum of that array. This particular problem, we'll notice right off the bat, is a little bit different from the transformations that I've described, because although it has a fairly large input data set of size 100,000, the output data set is actually just a single, and that's what's contained in the variable sum. And so this looks a little bit different than some of the problems that we've dealt with in the past. In fact, many of the problems that we've dealt with in the past, I would put into the category of transformational problems, which I'm describing on the left-hand side of this slide. A transformation, according to my definition, is characterized by the fact that the output data set size, in this case the array C, is roughly the same size as the input data set size, in this case roughly the array A. When we have a problem of that type, we very often find that it's relatively easy and straightforward to write the CUDA code to perform that operation in parallel. And I'm going to introduce a new piece of terminology, which is really just something I cooked up. You're not going to find this canonically in CUDA programming literature, but I think it's a useful way to summarize a particular idea, and that idea is the thread strategy. In other words, what should each thread do? What should each thread be responsible for? Any CUDA programmer that sits down to write a brand new CUDA kernel is immediately faced with this question, and it's part of the process of understanding the parallel decomposition of the work that you're trying to accomplish. And so initially when you set out to write a CUDA kernel, whether you know it or not, you are thinking about the question, what should I have each thread do? Because I know from what we've learned already that when I write a CUDA kernel, I'm roughly speaking writing a single thread code. I'm writing the code from the perspective of a single thread, and that code defines what that thread will do. And the CUDA parallelization process, the kernel launch and the grid dimensions and all the mechanics associated with that, will parallelize that thread code across a large number of threads. And in so doing, I accomplish my work in parallel. And so when I sit down to write a new CUDA kernel, I'm faced with this question: what should each thread do? Because that's going to direct my code writing efforts. And so when I have a transformational type problem, a very common thread strategy is to say I will assign one thread per output point, and therefore the definition of what each thread will do is simply to say this thread must do all of the calculations necessary, whatever that implies, to produce a correct value for this output point. And then I simply multiply that thread, if you will, across the grid. I expand that thread definition to apply across the entire grid. I launch that CUDA kernel, and since I have one thread per output point, if I launch enough threads, I end up populating my entire output array that way. It's a very straightforward thread strategy. It's a very typical CUDA programming model, and it works very well when you're dealing with problems like we've looked at so far, such as matrix multiply or such as vector add. Those problems naturally fit into this transformational model, and they work very well with this kind of thread strategy. However, on the previous slide, we have a different code realization. And if I simply naively said, I'm going to use the same thread strategy, I'm going to assign one thread per output point to this problem that I'm now defining as a reduction problem. A reduction has the characteristic that the number of output points or the size of the output data set is substantially smaller than the size of the input data set. Very often, a reduction problem might have an output data set of just one element, a scalar. So that's a characteristic, that characteristic indicates immediately that the problem that we're dealing with is a reduction. And if I use the same thread strategy in a naive fashion, in other words, I would like to assign one thread per output point, I quickly observe that I only have one output point, and therefore I'm only going to use one thread. And the realization that I would use then, if I was going to proceed down that path, is to use exactly the same serial realization with the for loop that I observed on the previous slide. And of course, we know from our previous treatment of CUDA, the last two sessions, that if I were to run a kernel with just one thread, I would almost certainly observe disappointing performance. It's not the way the GPU is designed to work. CUDA doesn't teach you to write kernels that way. So this thread strategy that works very nicely for transformation problems completely falls apart when I deal with a reduction problem. So what are some other thread strategies that I might come up with? Well, I know that I would like to have a lot of CUDA threads to work on my problem. So is there any way that I can assign one thread per input point for the problem on the right-hand side? Is there any way I can decompose the work that way? Because if I could, then I would immediately be able to start out with an array of threads, in other words, a grid that's the same size as my input data array. And if it's large, like we had in the previous slide, that might be a very interesting parallelization strategy. So let's take a look at that. If we decide that we want to assign one thread per input point, we might write some CUDA kernel code that looks like what I've depicted here in blue. I have a variable C. It's a pointer to a location in memory, so I'm using *C. And I'm going to say that each thread will take the value that's in C and will add its assigned input point, in other words, A of I, to it. Okay? And if we wrote a CUDA kernel that way, that would be a very, very simple kernel to write. And what we would observe is that it basically doesn't work. We'd observe that the variable C ended up with a result which was not the correct sum of our array A. Let's take a closer look now at why that would be the case. In order to do this, we're going to have to dive into some lower level behavior of the GPU. When we write CUDA C code, that's just a representation of what we're asking the GPU to do. And the compiler translates that into instructions that are actually executable. In other words, that are a part of the instruction set architecture of the GPU, that the GPU can execute so-called natively. And so that process is that process of converting C code to native code, if you want to call it that, is what the compiler is all about. The compiler does that. And we saw a little bit of an example of this a couple sessions ago when we were looking at the low-level thread scheduling behavior. I gave you an example of what that vector element-wise multiply might look like in machine code, and we saw that there were a couple load operations and there was a multiply instruction. In this case, the low-level machine code might look like what I've depicted here. First of all, I need to load for a given thread, I need to load its value from the input array, we're calling that A of I need to put that in a register. I'm also going to need the value of C in a register. In other words, I have to read it from memory, and I have to load it into a register R1. Once I have those two operands in register R1 and R2, I can add them together, which is also a necessary part of this sum reduction process. And I can store the result in R3, and then I'm going to have a store command that takes the value of R3 and puts it into the location indicated by the pointer C. So I'm doing a load of my input, I'm doing a read of C, a modification of C, and a write back to the variable C. And if we do this across a number of threads, what we observe is all of the threads complete the first instruction correctly. They each load their independent element, their input element from A of I into R2. But then as they load and modify C, we end up with some trouble. The threads are basically stepping on each other because every thread is trying to do this, and potentially every thread is trying to do this at the same time. And so this raises a whole bunch of questions. For example, in the last step, what happens when multiple threads try to write to the same location in memory? That is basically not sorted out for you by CUDA. CUDA doesn't have any special mechanisms, the way that we've written this code here, to handle that and sort that out in a coherent way. And so we end up with undefined behavior in the last instruction here, even if we ignore some of the problems that arise with the previous instructions. Another way to say this simply is that the CUDA does not enforce any order of thread execution, and so if your code would depend on order of thread execution for correctness, then your code is not correct unless you impose order. So how might we impose order in this situation? Well, we're going to take advantage of a special type of instruction which is available on the machine. It's part of the instruction set architecture, and it's also exposed in the C programming, or the C++ programming language that we call CUDA C++. And that is what is referred to as an atomic operation. What does that mean? It means that we have a new instruction that replaces 3 instructions in our previous instruction stream. So we're going to write a different piece of code that I've depicted in blue at the top of this slide. And that code replaces our previous line of code from the previous slide with this new thing called atomic add. An atomic add takes 2 parameters. It takes a pointer to a location to modify, that's the first parameter, and it takes an item to add to that pointer, a value to add to that pointer. In this case, we're passing A of I. We assume that I is our globally unique thread index. And so when we run this atomic add across a number of threads, it's going to do something special across those threads. And in order to understand what's special about it, we need to again look at the decomposition of this into machine code. So I'm depicting the previous machine code on the left-hand side of this slide. And what we're seeing on the right-hand side of this slide is that the initial instruction, the load of R2 with A of I, that is the same. That's unaffected by this transformation that I've done in C++ to use atomics. But the remaining 3 operations that I would have realized with the previous realization are now replaced with a new instruction, a machine-level instruction, which is basically an atomic instruction. It actually shows up as what we call a reduction, but a reduction is a form of an atomic instruction at machine code level. And so the instruction that I'm depicting on the right is a single machine code instruction, and it's what we call a read, modify, write. It does all 3 operations atomically. By that, I mean indivisibly. When the read happens, the modification happens, and the write happens, and nothing else is allowed to intervene. No other threads, no other activity are allowed to touch the location indicated by the pointer C in this realization. That's what we mean by atomic. It's indivisible. Nothing else can interfere or intervene. So in order for this to work, there's some things that may be not obvious. First of all, this serializes thread behavior. Previously, we had a situation where all threads were attempting to access the same location at the same time, and we declared that that is undefined behavior in the CUDA programming model. When we use an atomic to modify the same location instead, this now becomes well-defined behavior, and the way to think about this from a programming perspective is that the behavior amongst threads is serialized. The atomic hardware is implemented actually in a place called the L2 cache. And so when the atomic instruction is launched by a thread, there is a harmonization executive, if you will, in the L2 cache that looks at all those atomics and processes them one at a time. And so we can see now that with this atomic add operation, every thread is allowed to independently load its value of A, the A matrix or the A vector. But then each thread must get in line. Each thread serializes its behavior due to the atomic mechanism. And the first thread, whichever one it is, it doesn't matter, reads the location of C, adds its value, and writes the location of C. Then the next thread reads that location of C, picking up the new value, adds its A of I to it, and stores it back into C. Then the next thread does the same thing, and so on, until all of the atomics are resolved. So this atomic hardware is very useful for this type of operation. It serializes the operation, but it results in defined and predictable and expected behavior. The serialization of the thread operation, when multiple threads are attempting to update the same location using atomics, the serialization of behavior may have performance implications. In other words, we should generally not expect atomics to be able to proceed at the same rate as ordinary memory operations. And so we're trading off here. We're trading off performance for predictability and correctness using the atomic hardware that's built into the GPU. There's other types of atomic operations. Atomic add does what it says. It takes the value that's passed to it and adds that to a particular location in memory. There's also subtract, which subtracts the value. We also have a min and max operation, so we can find the maximum of the two values, replacing the location in memory with the maximum of what was already there and the value that's presented. And we can do the same thing with minimum. We have some other atomic operations as well, increment, decrement, which have a rollover behavior. You can read about these in the programming guide. And finally, we have a couple different types of atomics. First of all, we have atomic exchange and atomic CAS, or compare and swap. So atomic CAS is a conditional comparison of a value in memory to a given value, and if it matches, then the value in memory is replaced with the new value. So atomic CAS is typically going to take 3 parameters, not 2. And many, many other types of complicated and interesting atomics can be built using atomic CAS. So atomic CAS is sort of a basic building block atomic that can be used to build other types of interesting atomics. For example, an atomic operation that works on half of a value, half of a 64-bit value, but updates the whole 64-bit value, for example. That's an interesting type of atomic operation that could be useful in some situations, and you can build that using atomic CAS, for example. There's also atomic bitwise operations, which will operate in a bitwise fashion using Boolean arithmetic on locations in memory. Also, another thing to be aware of with atomics is they are limited in terms of the data types that they can actually work on. We know that GPUs can very often work on 64-bit floating point, 32-bit floating point, in some cases 16-bit floating point, and they can also work on 64 and 32-bit integer quantities directly. Those are sort of what I would call plain old data or native data types for CUDA C++. Atomics do not necessarily work on all of those data types. And actually, the footprint, the data types that a particular atomic operation will work on may vary by GPU architecture. So if you're going to get into using atomics, I would encourage you to pay attention to the programming guide section, which details this out. All of the information you need is contained in a very concise fashion. It's relatively easy to use, plenty of good information there. You can do other things besides just reduction operations with atomics. Obviously, atomics can be in a very straightforward fashion, as we've depicted already, can be used to perform various types of reduction. For example, we looked at a sum reduction, taking an array, a large data set, and producing a single number that is the sum of all the elements in the array. But there's other types of reductions. For example, a max finding reduction would take all of the elements in the array and find the maximum value. Again, that's a single quantity. It fits our definition of reduction, but it's not a sum reduction. It's a reduction that's finding the maximum. You could do the same thing with the minimum, And there's probably other arithmetic operations that you could do on an array that would fit the pattern of reduction and might be amenable to atomics. However, there are some other things that we can do with atomics that don't obviously, they're not immediately evident that they are a reduction style operation, although you might connect the dots. For example, we can use an atomic to pick the next item off of a queue. We would have a variable that represents the next item in the queue, and any thread that wanted the next item in the queue would use an atomic add operation on that variable. One of the things that we haven't talked about yet is that atomics return a value. That atomic instruction that I showed 1 or 2 slides ago takes some parameters and it updates a location in memory, and very often it might be used just for that purpose. But an atomic also has a return value, and the return value for an atomic, quite simply, is the old value in the location. So an atomic is a read, modify, write operation. The first thing it's going to do, or one of the first things it's going to do, is read the location in memory that you've indicated, the location that is potentially going to be updated. That red value, that's the first step in the read, modify, write operation, we're going to declare as the old value that was in that location. And most atomic functions return that old value as their return value. So if I do an atomic add on a location in memory, which is indicating the next item in a queue, and let's say I add 1 to it, then the atomic operation will add 1 to that location so that anyone else who comes along won't pick up the queue slot item that I picked up. Instead, they will pick up the next one. And furthermore, the return value of the atomic will be the value in memory before 1 was added to it. In other words, it will be the value in memory that refers to the top item in the queue, the one that I'm going to take and work on. So that's an example of using an atomic to determine the next work item, queue slot, or in other respects to order operations amongst multiple independent threads. And it's a very simple, typically can be very simply done with atomic add. Another type of thing that we can do with an atomic is to reserve space in a buffer. This is extending a little bit the previous idea. And what we're going to do is declare that we have a buffer, an allocated area in memory, and we now want to imagine that we have an algorithm that is producing a varying amount of data per thread. Let's say that we have an algorithm that's looking at a large array and looking for matches to a particular value. And when we have a match, we want to record the index of that match. We want to capture that. And so what we have is a very large array, a match value, and we'd like to have presumably a smaller array that has the indices of the locations where that value is found. We want to do this in a thread parallel fashion, so we're going to take up this large array and we're going to break it into pieces and have each thread work, or each thread block, let's say, work on a piece. And therefore, each thread is going to have a set of locations that it's going to be looking for a match, and it may or may not produce matches in those locations. So any thread might produce 0, 1, or more matches based on the amount of memory that's handed to it. And therefore, any thread might have 0, 1, or more locations in the output array that it wants to populate with an index where the matching value is found. This could seem a little bit challenging to a CUDA programmer, and one of the straightforward ways to do this is to simply allocate an array to collect the indices that's the same size as the input array. We know in this particular case that this problem has an upper bound where the total number of locations needed for the output cannot be bigger than the total number of locations for the input. But that still leaves us with problems like how to compact the data, how to get rid of empty spaces, and how to read it in a simple fashion. And so can we do better than that? One of the ways that we can do better than that is to use this kind of method to have a buffer that's pre-allocated, and each thread will reserve, once each thread figures out how many locations it needs and has its own local array of the indices that it needs to record, then it goes to the buffer and reserves space in the buffer. And the way that it reserves space is, once again, to use atomic add. But now, instead of adding just 1 like we did in the previous example, we're going to add the data set size that corresponds to the number of indices that my thread has found. So if my thread has found 3 indices, then my D size here is going to be 3, and that's the value that I want to add to a buffer index, which is a location of the next empty spot in the buffer. And when I add that, then I will have updated the buffer index pointer, or the index, I should say, the buffer index. I will add that to the buffer index, and so the next thread that comes along and wants to reserve space is going to be working after the end of my reservation. But I now have the buffer index, the old value, as the starting point for the locations that I am allowed to use, in other words, that are reserved for me, for my thread in the buffer. So this is an example of a way to use atomics to basically do something that we could refer to as a stream compaction operation. And so if you Google stream compaction, you will find that it's not a trivial, it's a fairly trivial operation to do in a serial fashion from a single thread, like you might write as a C or C++ programmer. But if you want to do it in a parallel fashion, stream compaction immediately becomes non-trivial, and there's some canonical techniques. I'm not suggesting the atomics is the best way to go, but it's one possible approach. Okay, so that concludes our treatment of atomics. And what we did was we used a motivating example, in particular a reduction, to motivate our analysis of the use of atomics and what they're good for. But we also observed that atomics may have the characteristic that they may be constrained in terms of performance. We haven't gone into details, and I don't intend to go into details, but suffice it to say that we should assume as a CUDA programmer that atomics might not be able to operate on memory at the same rate as ordinary memory operations. They're certainly a nice vehicle, and they help us to sort out certain problems in a very simple way, but they may not be the most performant option that we have. And so there's another technique for doing reduction operations, which I'm going to refer to as a classical parallel reduction technique, and that's what we're going to look at next. And as we'll see, a classical parallel reduction doesn't necessitate the use of atomics. It may, we'll get into that, but it doesn't necessitate the use of atomics. So we're going to go back and look at essentially the same problem again. We have an array, and we'd like to get the sum of that array. That's a reduction according to our definition. It takes a large size input data set and produces a single valued output data set. And we would like to come up with a method that's not limited by atomics, and also a method that, at least at the start, can use as many threads as possible. Ideally, when we're a CUDA programmer, we know that we want to use lots of threads to realize our algorithms, and we'd like to apply that methodology to reduction as well. So we'd like to have a strategy here, an algorithm that allows us to use lots of threads, especially if the input data set size can support it. As we've discussed already, reduction techniques are commonly used, and they're an important programming concept to have under your belt. If nothing else, when you're a CUDA programmer and you're faced with a challenge, you would like to be able to differentiate reductions versus transformations, because then when you're coming up with your thread strategy, you won't make some obvious mistakes. You'll immediately recognize that, hey, this is a reduction problem. It fits the definition, and therefore I need to think differently about it. Just having that level of awareness as you're diving into CUDA programming is going to benefit you as a CUDA programmer, okay? And so parallel reduction is a very common programming technique. It's a common programming challenge that we face, and understanding how to do it correctly allows it to become an important data parallel primitive for you, an important skill to have in your toolbox as a CUDA programmer. We're not going to spend too much time on naive implementations, but naive implementations or incorrectly done implementations will often run into bottlenecks. And so we want to avoid those from the get-go. The basic methodology we're going to use is a tree-based approach. So what we're depicting here at the bottom of the slide is an input data set in the orange bubbles on the top row. And we can see that we have 8 items in that data set. Our objective, of course, is to add all of those together. However, we can decompose this problem using a tree-based approach. So we're going to use this tree-based approach to decompose the problem into steps to get to our final answer. And those steps are going to involve pairwise additions of results from the previous step. So initially we have 8 items. In our first step, we're going to do a pairwise addition, 2 items at a time. and we're going to produce 4 intermediate results, 4, 7, 5, and 9. Those are sums, pairwise sums of the previous input data set. This now takes our data set from 8 elements and reduces it to a set of intermediate results of size 4. With a size 4, we can again do pairwise additions, and we reduce our data set to a size of 2, 11, and 14. And in our final step, we do one more pairwise addition to produce our final result, 25. So this, of course, ends up with a single operation, but it starts out at least with a set of threads or a set of operations that's comparable, that's on the order of the size of our input data set. So this is interesting. We now want to figure out how to realize this in CUDA. And in order to realize this in CUDA, or a massively thread parallel approach, which is what CUDA is, one of the problems we're immediately going to run into is the need for global synchronization. What does this mean? Let's go back to the previous slide for a moment, and let's observe something. I would like to focus on the operation that produced the result 11 on the lower left-hand side of this tree. That operation added 4 and 7 together. 4 and 7 were produced by the previous operations that added 3 and 1 and 7 and 0. Let's suppose that we have threads executing in no particular order. So the 3 and 1, the thread that's responsible for adding 3 and 1 produces its value, which is 4. And let's say that we now intend that thread to go on and add 4 and 7 to produce 11. That might be possible. What if the thread that's responsible for producing the result 7 hasn't executed yet? Because again, CUDA imposes no particular order of thread execution. If you need an order, you must impose it as the programmer. So if we don't impose any order on this, the thread that added 3 and 1 together to get 4 might race ahead and attempt to add 4 and 7 to get 11, but when it went to get 7, that result hadn't been produced yet, because the thread that was responsible for that hasn't gotten to that point. So we're going to need synchronization. We're going to have to impose order, and the order that we want to impose is we would like the first set of operations, in other words, the top of the tree, all of those operations to be done before any operations at a lower level of the tree are allowed to begin. Since this synchronization, therefore, is imposed across the entire width of this tree, which is kind of like saying imposed across the entire width of our grid, we would refer to this as global synchronization. And an analysis of the operation that we've described on the previous slide immediately gives evidence that we're going to need a global synchronization mechanism if we're going to make this work in a thread parallel way. So we then have to ask, are there ways that we can synchronize across all threads? Not just all threads in a thread block, because we have a tool to do that already. It's called sync threads, and we've used that already. That works great in a thread block, but actually we need this across the entire grid, across all thread blocks. Okay? There are some solutions to this. One of the solutions is we can decompose each tree operation, each level in the tree, we can decompose that into its own kernel. When you launch a kernel in CUDA, we haven't gotten into this in too much detail, but when you launch a kernel in CUDA, and then you launch another kernel after it, those kernels, if you don't do anything special, which we'll talk about in a future session, those kernels will serialize. CUDA will, if you don't give it any other instructions, CUDA will issue the work in the order that you issued it. It will execute the work in the order that you issued it. In particular, if I launch 2 kernels, one after the other, the second kernel will not begin until the first kernel has completed. And so we say that the kernel launch boundary is a global synchronization point. What that means is, when I get to the end of the kernel launch boundary, in other words, when that kernel completes, I know that all threads are complete. And therefore, that's effectively a global synchronization barrier. And so one of the possible solutions is to decompose the tree, if you will, into a set of kernels, a set of kernel launches perhaps, one kernel launch per level in the tree. And as a result, the kernel launch boundary gives us our global synchronization, and that works. We're going to get more into the details here, so bear with me, but nevertheless, that mechanism works. The kernel launch process itself has some overhead. It's not zero. It's generally speaking fairly low overhead relative to processing time. And so if you have a kernel that's doing a lot of work, the kernel launch overhead might not be a big deal. But nevertheless, it's something to be aware of. And as we see when we decompose this into multiple kernels, towards the end of the sequence, the width of those kernels, in other words, the grid associated with the kernel launch, gets small because the width of my tree shrinks as I go down the tree. So we'd also like to consider, are there any other possible solutions? Yes, there are other possible solutions. The one that we will advance, since we've just learned about atomics, the one that we will advance is the possibility to use an atomic operation at the end of our tree reduction in order to effectively synchronize across thread blocks. There are other approaches which we won't talk about. One of those is to use a thread block draining approach. What this means is, once again, we're going to use atomics, and we're going to acknowledge that at the end of the kernel, we know that the threads blocks are retiring one by one. They're completing their work and finishing. We can actually keep track of that activity using atomics, and using atomics, we can identify which thread block is the last to complete. Once we've identified the thread block that is the last one to complete, we can now task that thread block with additional work, knowing that all other thread blocks are complete. Therefore, we've got a synchronization boundary, and we can complete the final reduction steps using that thread block alone. That would be called a thread block draining approach, and there's a CUDA sample code that details how to do that. The last approach is to use something called cooperative groups. Cooperative groups is a topic that we will cover in a future session. I think it might actually be our last session, maybe in September. Just briefly, cooperative groups is a fairly recent addition to the CUDA programming model that addresses the fact that the CUDA programming model allows for decomposition using a fairly coarse structure. Basically, the structure that we're given is the thread block. So we decompose our entire kernel into a thread block, and from there, we don't really have any well-defined decomposition of a thread block. We've talked about warps, but warps are not actually part of the CUDA programming model. So what cooperative groups does generally is to address the fact that CUDA doesn't provide a rich set of constructs or primitives to do thread cooperation and thread decomposition, thread group decomposition. And cooperative groups provides a new set of intrinsics and primitives that allow us to build more flexible sized groups of threads that can cooperate together, that can work together. And we know just from our study that we've done already that one of the ways that threads work together is by communication, and another way that threads work together is through synchronization. In fact, those two often go together, and they go together in the case of the reduction that we're about to investigate in more detail. Cooperative groups gives us additional flexibility along those lines, and one of the things that cooperative groups provides for is a grid-wide sync, a brand new thing in CUDA. So that's the third way, and if you want to learn more about a cooperative group-based method, then stick with us at least to the end of this training sequence, which would be, roughly speaking, in September, thereabouts. So we're going to focus on this first one. As an example, to eliminate a sequence of kernel launches to perform our grid-wide synchronization, we're going to use a single kernel launch to perform, let's call it the top level of the tree. Actually, the tree gets partitioned both horizontally and vertically. And then we're going to use atomics to resolve the partial sums or the partial reduced values that need to be reduced one more time. So let's take a look at that from a coding perspective. What I've depicted in the upper left-hand corner here is a fairly condensed, a bit dense, but it's a complete reduction operation, a complete what we would call a sweep reduction. And hopefully when we work through the information on this slide, why we would call that a sweep reduction becomes evident. So first of all, there's a for loop. The idea behind the for loop is that we are iterating downwards in the tree. As I mentioned, our strategy here is going to be to divide the tree both horizontally and vertically. The tree that I'm talking about is the tree that we depicted at the bottom of this slide. So it's important for you, hopefully, to keep that as a mental model. And this tree has a horizontal dimension from left to right and a vertical dimension from top to bottom. The vertical dimension from top to bottom, as we traverse that, we're traversing through iterations of reduction. We're collapsing the tree to smaller and smaller numbers of partial sums in this case. Okay? But we can partition this tree horizontally as well. We can take the first set of values on the left-hand side and assign that to a thread block. We can take the next set of values and assign that to another thread block. The next set of values as we move to the right to another thread block, and so on. That's what I mean by horizontal decomposition of the tree. So both of these things are happening, and they're both happening in this code. In this code, we're imagining this code is running at a thread block level for understanding. Of course, it's running in multiple thread blocks, but each thread block is responsible for a left to right partitioning of the tree, a horizontal partitioning of the tree. So we're taking a set of elements, we're assigning it to a thread block, and saying to that thread block, you do everything that's necessary to reduce that subset of our input data set to a single value. In the process of doing that, this thread block will iterate downwards through the tree, and that iteration downwards is encapsulated in this for loop. So the for loop is going to start out and it's going to declare a variable s, which is equal to the block dimension divided by 2, so half as many threads as we have in the thread block. And then for every thread which is less than that dimension, so if it was a thread block with 64 threads, it would be the first 32 threads past the if test. For every thread that passes that if test, that thread will take a value in shared memory and add it to another value in shared memory. And the values that are being added together are indexed using the same thread ID. So thread 0, for example, will take the value in location 0 in shared memory, indicated by S data, and it will add to it a value that's 0 plus S. In other words, if S was 32, it's 0 plus 32. So we'll take the 32nd element and add it to the 0th element. Thread 1 would take the 33rd element and add it to the first element. Thread 2 would take the 34th element and add it to element index of 2, and so on. These threads ostensibly are operating in parallel. They don't necessarily have to be operating in parallel. We know that threads really operate at the warp level, and so the threads within a warp are truly executing in lockstep, and other threads in the thread block may not be. But nevertheless, our concept here is that these threads are performing this particular if statement, including its body, which is adding elements in shared data, in shared memory. It's as if it's working in parallel. And we're depicting that on the right-hand side with our first sweep operation. So we see a bunch of orange circles. Those are our partial sums. The values in shared memory are depicted across the top, and each thread is taking its corresponding value and adding to it another value in shared memory and storing the result back to shared memory. Okay, that's what we're depicting using the arrows here. And you can see there's a sweeping operation. We're sweeping from the upper values to the lower values. Okay, once we do that, we need to make sure that all threads in the thread block complete that operation before we allow any thread to proceed. Therefore, the step that we're going to use is sync threads. We learned what that does already. It does exactly what I just described. And note here that sync threads is outside the if statement. The if statement, the body of the if statement is whatever's in the curly braces. The sync threads is outside that. So initially we're selecting a subset of threads at each level of reduction. We're selecting a subset of threads to actually do the sweep operation. And then we're making all threads in the block wait for every thread to complete. Once we're done with that, then we go back and iterate again on the for loop. And as we iterate on the for loop, then we move downward on the right-hand side diagram. And instead of, in this example, instead of having 8 additions to perform, in our next iteration of the for loop, we divide our S variable by 2. And therefore, we have 4 elements to add, or 4 sets of additions to perform using 4 threads. And then we get through our next iteration of our for loop, we divide S by 2 again, and we have 2 additions to make, finally 1 addition to make, and the end result is the first location in shared memory at the bottom on the right-hand side. The first location, 41, has the sum of all the input values. This, therefore, this value of 41 is a partial sum. It's the final result of this for loop. You could sort of imagine it as the final result of this thread block, and it's the partial sum that represents the sum of all the values that were assigned to that thread block. And we used a set of threads operating in parallel, subdividing at each step in order to produce this partial sum. This is not the only indexing pattern you could use to make these sum operations happen. For example, I could add adjacent elements, not unlike what I depicted in the actual tree that we looked at on a couple slides ago. I could have thread 0 add locations 0 and 1 in shared memory, and I would have to make a similar decision for thread 1 and so on. There's a lot of different indexing approaches that I could choose. Most of them are suboptimal in some way. We're not going to go through all the details of why those other choices are all each individually suboptimal. The reasons for their suboptimality vary depending on your exact indexing pattern. But this sweep indexing pattern avoids most of the kinds of suboptimality that can enter into a parallel sweep-based reduction. This particular indexing pattern is a canonically good one. And one of the things that it avoids is bank conflicts. And so we learned about what bank conflicts are 2 sessions ago. They're a particular performance concern associated with using shared memory, not a correctness concern. You'll still get the correct answer. But bank conflict can cause your shared memory to operate slower than what it might otherwise be able to do in terms of data throughput. And so this particular sweep pattern is basically avoids bank conflicts. Let's take a bit of a detour because what we're trying to do now is assemble a complete kernel, if you will, a complete reduction operation. What we looked at on the previous slide was just a code snippet. It's just the for loop. We want to look at all of the steps that are necessary to create a complete sum reduction operation. And in order to do that, we want to introduce a new concept. And this new concept is called a grid stride loop. The idea here, the goal, is that we'd like to be able to create kernels that can work with a decoupling between the size of the kernel, in other words, the grid, the size of the grid, how many threads are performing my operation, and the size of my data set. I would like to be able to, for reasons that may not be that obvious right now, I would like to be able to write a kernel and launch a kernel with a particular complement of threads and have that kernel do the correct operation, whether my input data set is smaller than the number of threads, the same as the number of threads, or larger than the number of threads that I use. Some of the motivation for why I might want to do this has to do with performance optimization. It's performance optimization down in the 1% to 5% level. But nevertheless, there are coding ninjas out there that go at that level of performance. And so a grid stride loop might be something that allows you to optimize the thread complement for my particular GPU, just as one example. It's not the only reason to use grid stride loops. One of the big important reasons is just for programming flexibility, to make it easy to write correct code that works in a variety of situations. So in order to construct a grid stride loop, what we're going to do is imagine that we have a grid that has a particular width. And we're going to have that grid perform whatever operation it's performing, whatever kernel code you have written, on an input data set size that initially corresponds to the width of the grid. When the kernel, when that operation is done, when we have processed that first, let's say, 4 elements, which is our grid width here, just making numbers up, not a sensible number, then what we're going to have to do is have the entire grid, in other words, all the threads in the grid, stride to the next locations in memory that we're going to process. And in so doing, we're going to process the new data, and we might be adding that data to the data that we've accumulated already, for example, like what we're about to do with a reduction operation. But it doesn't have to be a reduction. A grid stride mechanism can be used on transformation problems as well to good effect. So the idea, quite simply, is we're going to have a number of threads. You could think about it as a fixed number of threads if you want. A fixed number of threads, a predetermined number of threads that is equal to the width of my grid. And those threads will initially process a size from the input data set that corresponds to the grid width. When they're done processing that, they will stride, they will add an index value to their operation, and then repeat the operation using the next chunk of data. We call this grid striding, and we call the general methodology a grid stride loop. In other words, we will observe a loop in our kernel code that is causing the indexing to be adjusted in exactly this way. And I've depicted an example at the bottom of this slide. So at the bottom of this slide, we're initially starting with a globally unique thread index. And remember, our grid now may not be the same. It might be smaller than our input data set size. And I'm going to create a while loop, which will look at the index. Remember, this is operating per thread. It will look at the index value of that thread and ask the question, is it less than n being the entire size of my input data set? And if it is, it will allow the loop operation to perform. In the loop, at the bottom of the loop, we will update our globally unique thread index to make this thread now jump or stride to a new location. The thread isn't moving. There's nothing fundamentally that's changing here. We're simply changing a variable, our IDX variable. Okay, so we're adding to our IDX variable, and the amount that we're adding is the total number of threads in our grid. We can achieve that value, that calculation, quite simply using built-ins as I've depicted here. So griddim.x times blockdim.x for a one-dimensional grid gives us the total number of threads in the grid. Griddim.x is the number of blocks in the grid. Blockdim.x is the number of threads in a block. When I multiply those two together, I get the number of threads in the grid. If I add that value to my previously computed globally unique index value, all threads adding the same amount, then all threads move by the same amount in terms of the element that they will process next, and we call that a grid stride. Each thread then starts the while loop over again and checks to see if its new strided location is still within the data set. If it is, the processing completes, and that particular thread will stride again. Eventually, every thread will stride off the end of the data set. Eventually, IDX less than n will be false for every thread, and at that point, this loop will terminate on a thread-by-thread basis. If we look at what's actually going on in the loop here, this would actually be applying a grid stride loop to a reduction operation. So you can imagine S data is shared memory, TID is the thread index, IDX is the global index, and for each stride of the loop, each thread is calculating its own running sum of a subset of the input data that thread is responsible for, and that running sum is contained in S data of TID for that thread. And so each thread is striding through global memory, striding through my input array, taking selected values from that input array and adding it to its running sum. Each thread then ends up with its own running sum, and each thread can then begin, after this while loop is complete, can then begin the parallel reduction, the sweep reduction that we depicted on the previous slide. Okay. Let's continue, because what we're trying to do is assemble a complete kernel now for you to look at. So this is what a complete kernel might look like. We're defining a TID variable. That's just the same as thread IDX.x. We're going to initialize our shared memory array to 0. That's the initialization of each running sum for each thread. We're going to create our globally unique thread index. We can now think of this as a starting point for each thread, the starting point that it will subsequently stride from. And then we're going to use a grid stride loop so that my grid can process, in other words, absorb, in other words, create partial running sums across the entire data set, more or less independent of the size of my grid. This will work if I have one thread in my grid. It'll work if I have 2 threads in my grid. It'll work if I have 100 threads in my grid. It'll work if I have 1,000,000 threads in my grid. It'll work if I have 1,000,000,000 threads in my grid. Independent of the data set size n, does not matter. This grid stride loop will give me the correct result, the correct set of partial sums. Once the grid stride loop is complete, I can then dive into my parallel sweep reduction. You'll notice that I've reordered sync threads and my sweep operation, and that's to account for the fact that I have been doing shared memory operations in my grid stride loop. So before I get into my parallel sweep, I want to make sure that all of this updating of shared memory in the grid stride loop is complete before I begin combining the partial sums that this thread block has accumulated using my sweep reduction. But nevertheless, these two code blocks here are quite similar to the two that we built up on the previous slides. One for the parallel sweep reduction, one for the grid stride loop. When all is said and done, as we pointed out, the sum reduction across this entire thread block ends up in the 0th location in shared memory. So if my thread ID is 0, then I'm going to write my thread value, in other words, the shared data in the 0th location, in other words, the parallel sum reduction across this entire thread block. I'm going to write that out to a location in global memory. And each block now is producing its own partial sum, and therefore I will need enough locations in my output array out to record all of the partial sums across all of the thread blocks. So I'm using blockindex.x to index into my out array. And what I end up with in global memory at that point is still a set of partial sums. And so I would need another operation. Perhaps I could launch a kernel like this again on those partial sums. What I suggested previously, though, is that we'd like to consider ways that we could get this done in a single kernel launch. And so the way that I'm going to advance here, not the only way, we talked about thread block draining approach. We also talked about cooperative groups. But the way I will propose here is to replace that final operation with an atomic add. Okay, now we can do an atomic add to a single location out across all the thread blocks with our shared memory data value in the 0th location. And what should end up in out when this kernel is done is not a set of partial sums, but the final sum across the entire input data array. This sort of operation, this sort of transformation, refactoring, to use an atomic at the end, will drastically reduce the pressure on the atomic system. The previous portion of this thread block and every other thread block is striding across global memory, efficiently adding data together using the most efficient techniques that we know of. And it's reducing a very large data set to a small data set, in other words, a set of partial sums, one per thread block. Now, the pressure on my atomic system is reduced to just one partial sum, in other words, one value, in other words, one atomic operation per thread block. So that's a significant reduction, and that sort of optimization might make a lot of sense. It might actually be best from a performance perspective by reducing the pressure on the atomics to that level. It's not the only way, as we talked about, and one of the possible considerations here is one that I pointed out when we talked about atomics. I said that atomics don't do everything. They don't necessarily work on any sort of data that you can imagine. Some atomics are not supported on double floating point operations, for example. So if I'm performing a reduction on double values instead of float, I might discover that there's not a convenient atomic that I could use here. Furthermore, especially if you get into the homework, in the homework we will ask you to write a different kind of reduction. And depending on the type of reduction you're doing, in the homework we'll ask you to write a max reduction, so there is an atomic max operation. But you might come up with a reduction operation for which the reduction operator is not something like sum or max. It's possible. And if you did, then atomics wouldn't really be a choice here, because you're ultimately going to have to be able to have an atomic that represents the type of reduction operation that you're trying to perform. For sum and max and min, we have atomics for that. But we may not have atomics for every type of reduction operation. And remember, what we're focusing on here is a methodology and a strategy. The important part of this is not the fact that we're summing elements together. Yes, we're doing that. But the important part is the structure of the code to allow many threads to operate in parallel. Those threads can operate in parallel whether we're adding things together or subtracting or finding maxes or doing other types of binary operations. In other words, two input operations. So the reduction operation can be generalized across a wide range of binary operations between values. And we can use the same strategy, the same coding strategy to achieve that. Okay. The last thing we'll talk about is warp shuffle. Warp Shuffle is another feature that was added in recent GPUs. It's really not recent anymore, but the first GPUs that appeared in the CUDA programming model didn't have Warp Shuffle operations, but all GPUs supported by current CUDA programming toolkits, Warp Shuffle is available in all of those. So what's the motivation here? What we've been doing so far is performing this reduction, our sort of motivating example from the beginning of this session. We've been performing our reduction using shared memory. And we know that shared memory is a vehicle to communicate data from one thread to another. That's one of its primary uses. And so in order to use shared memory in that way, it requires two operations. One thread has to write into shared memory. That's an instruction. And another thread has to read from that location in shared memory. That's another instruction. And we might actually require synchronization in between those, so it gets more involved. Wouldn't it be nice if there were a way to directly send data from one thread to another without using shared memory? Well, there is, and that methodology is called Warp Shuffle. So the idea behind Warp Shuffle is that it allows for these sort of direct thread-to-thread communication within a warp. We know what a warp is now, and so the warp is starting to emerge from the cloudy darkness into something that's more visible in the CUDA programming model. Warp Shuffle is an example of something that really takes the warp and makes it evident from the programming model. Okay, so it's now important for a programmer to know what a warp is in order to use Warp Shuffle. A warp is a set of 32 threads. It's a fixed decomposition of the thread block, which we described in a previous session. It's a set of 32 threads that essentially we could imagine them operating in lockstep. So the Warp Shuffle only allows for communication within a warp. One thread in a warp can directly send a value to another thread in a warp in a single instruction without using shared memory or memory of any kind. And there's different ways that we can define the pattern of movement. The most general way is to use an operation called shuffle sync. All of these operations have a suffix of sync, and that was something that was introduced with CUDA 9, so it's basically current for CUDA. All current CUDA toolkits that you're likely to use are going to require this sync suffix. Okay, so it's an intrinsic that says, first of all, my warp needs to be synchronized, so the sync suffix and the mask are what accomplish that. And the shuffle operation means that I can have direct thread-to-thread communications within the warp. So the most general one of these is shuffle sync, and shuffle sync allows each thread to specify the lane that it will copy from. Yes, each thread gets to select the lane ID that it will take its value from. There's other variants. Shuffle up and shuffle down are the next most obvious ones. Instead, with shuffle up and shuffle down, we specify a delta or an offset, and each thread applies that delta or offset to choose a thread who's either logically to the right or logically to the left of it in the warp. That's what shuffle up sync and shuffle down sync. And shuffle XOR sync is more complicated. It basically allows you to create a calculated pattern that uses the XOR operation on a bit pattern to select the warp that you're going to copy from. It was provided to allow certain types of reductions or certain types of operations, perhaps I should say, like a prefix sum, to be done at the warp level in a very concise fashion. But the most general of these is shuffle sync, and in that case, each thread needs to supply an index. A few other things to be aware of when you're using these intrinsics. Both source and destination in the threads in the warp need to participate. You can write conditional code. In fact, we looked at conditional code that causes some threads in the thread block, excuse me. We looked at some conditional code earlier in this session that causes some threads in the thread block to not participate. That was necessary for our sweep reduction, for example. If you had that sort of conditional code and that conditional breakpoint, that boundary, was within a warp, so if thread ID is less than 16, for example, would select the first half of the first warp, and it would prevent the second half of the first warp from participating, then you've now said that your shuffle operation can only work if the source and destination threads are within that range of 16. the first 16 threads in the warp, because you've prevented the other threads from participating using conditional code. If you do that, your mask operation has to be set accordingly as well. The mask parameter to the sync variance of these specifies which threads need to participate. Okay, let's continue. So how could we modify our previous code to use warp shuffle and therefore perhaps, let's say, reduce the pressure on shared memory? But how would we mechanically modify our previous reduction to take advantage of warp shuffle? Well, we're going to have a similar starting point, meaning we're going to use a grid stride loop. And now each thread, instead of keeping its running sum in shared memory, is going to keep its running sum as a local variable called val. Okay, so this is now a local variable. This is not a shared variable. It's local to each thread. Each thread has its own independent variable val. That's going to be the running sum. And now we're going to craft our grid stride loop so that it sums into the variable val. That's our starting point. That's conceptually quite similar to what we had done in our previous code walkthrough. You can see that we're defining some other variables. We've got our globally unique thread index. We're going to need that. We've got our local TID variable. We're going to need that. We have a mask variable. This is going to be used for the shuffle sync operations. And the mask variable is a 32-bit value that specifies which threads need to participate in the shuffle operation. And in this case, we're passing a 1 for each of the 32 bits. So we're stating right up front here that our shuffle operations need to use all 32 threads in the warp. We're also going to need some variables that I've called lane and warp ID. Lane means which thread am I in the warp. Thread ID, thread index.x, is a number from 0 up to the thread block size. But what I need also is a variable that tells me, am I the 0th thread in the warp, the 1st thread in the warp, the 2nd thread, and so on. When I have multiple warps in my thread block, in other words, the thread block size is larger than 32, then I'm going to have multiple warps, each of which has a lane 0, each of which has a lane 1, and so on. The other thing I'll need in order to make all this warp is a warp ID variable. In the situation where I have multiple warps, I need to know, am I warp 0, am I warp 1, am I warp 2, etc. And the need for these variables will become evident as we walk through the warp shuffle code. So the first step in our warp shuffle is to allow each warp to create a partial sum. And so this is what we're calling our first warp shuffle reduction at the bottom left-hand side. And you can see we're going to use a for loop. And initially this for loop looks a little bit sort of something like the for loop that we used in the sweep reduction. We're going to start with our warp size divided by 2. And as long as that variable called offset is greater than 0, we're going to iterate through this for loop, each time dividing the offset by 2. We did something similar in our sweep reduction. Then the only other item here in this first warp shuffle reduction is to take our val, this is a variable for each thread, and select another val using the shuffle down sync operation. Select another val item from another thread, that thread being indicated by the offset and the fact that this is a shuffle down operation. So that means for thread 0, it's going to take its val and it's going to add to it the val from thread warp size over 2, which is 16. So initially offset will be 16. So 0 will take 0 plus 16 and add them together and put it in the val for thread 0. Thread 1 will take its val and add to it 1 plus 16 is 17, and so on. So you can see conceptually it's very similar to the sweep operation, excepting it's happening at the warp level amongst each warp of 32 threads, and each warp is producing a partial sum, a single partial sum, and that single partial sum is ending up in the thread that is at warp lane 0 in that warp. So once we're done with our sweep reduction, which is just this very simple for loop, just one statement, then we have to say if I am lane 0, in other words, if I am the lane that has accumulated the partial sum for my entire warp, now I'm going to use shared memory, and I'm going to put my value into shared memory at an index corresponding to my warp ID. So warp 0 will have a location, warp 1 will have a location, warp 2 will have a location, and the maximum number of warps that I can have in a thread block is 1024 over 32, so that's 32 warps. And you can see that I've defined my shared data size to be of size 32. I can just use a fixed number here now. It's a relatively small amount of shared data, so I'm not too worried about using that much. So each warp will have its thread corresponding to lane 0, write its accumulated value into shared memory. And now we have to make sure that every warp has done that operation before we allow anyone to proceed. So we're going to use the sync threads operation, just like we had a sync threads in our sweep reduction in the previous example, for the same reason. We want to let the code entirely complete the first warp shuffle before we go on to the rest of the thread code. What we're going to do in the remainder of the thread block now is another warp shuffle, but the only warp that we're going to need is warp 0, because I now only have 32 items, a maximum of 32 items in shared memory. I'm going to pull those back into the warp, reload val from shared memory, okay? So I'm going to bring those back into local variables in the warp, and then I'm going to do one more warp shuffle reduction, which is now only operating on warp 0. And when that warp is finished with its final warp shuffle reduction, then it will have accumulated a single value in lane 0 that corresponds to the sum across the entire thread block, and we will then update our global value using atomic add like we did previously. So this is a complete realization of the previous parallel sweep reduction, but now instead of using a sweep through shared memory, we're primarily using sweep operations happening using warp shuffle. There are other things that we can do with warp shuffles besides just this kind of a sweep reduction. Well, first, let's talk about some of the benefits. First of all, we are reducing, or maybe for some realizations we might eliminate shared memory usage, but we've certainly reduced the amount of shared memory that's required per thread block. And this can be valuable. First of all, if you have well, the primary reason that it might be valuable is that by reducing the pressure on shared memory may become no longer a limiter to occupancy. I've briefly mentioned occupancy in one of the previous sessions. The total amount of shared memory used by my kernel can be a limiter to occupancy and therefore a limiter to performance. And we will touch on occupancy again in a later session on optimization. The other principal benefit is related to the instructions themselves, and in particular, we're taking advantage of the two things that I mentioned already. First of all, we have a single operation. It's an intrinsic. It's called a warp shuffle operation, but nevertheless, it's a single instruction at the machine code level instead of two or more instructions, and we don't require synchronization as each warp is performing its work. Once each warp is done with its work, then, as we saw, we loaded shared memory, and we did require synchronization at that point. So we can say we're reducing the level of explicit synchronization compared to the shared memory sweep, which required a sync threads at each sweep operation. At each iteration of the for loop, it required a sync threads. So we're reducing the instructions and we're reducing the amount of explicit synchronization. Some of the key benefits of warp shuffle, as we've seen in our parallel reduction. Briefly, some other things that we can do. It may or may not be obvious, but I can use a warp shuffle to broadcast a single value to all threads in the warp in a single instruction without using shared memory or loops or anything like that. I can do other types of operations. It's not that obvious. We won't go into it in this session, but I could create, instead of a reduction, I could create at the warp level a prefix sum. I can even do sorting at the warp level. So all of these operations, all of these primitives, data parallel primitives, are things that are more efficiently realized using warp shuffle, especially if I'm focused on operations across a warp, in other words, 32 elements, let's say. So many data parallel, we just looked at one, reduction, but many other data parallel primitives can be more efficiently realized at the warp level using warp shuffle, like a prefix sum, like sorting. The other thing we can do is use warp shuffle to benefit atomics. In many cases, there will be situations where I want to or need to use atomics anyway, and I may have a situation where each thread in the warp is doing an atomic operation on a particular value in global memory. So across a warp, that means I'm going to put 32 atomic operations into the queue, if you will. And that's a particular level of pressure on the atomic subsystem. Well, since I'm updating the same location, let's say it's an atomic add. Since all 32 threads in the warp are updating the same location, wouldn't it be clever if I could first add all 32 elements in the warp together and then just do one atomic operation on the location in memory? That concept is called atomic aggregation, and atomic aggregation is something that you can do in a fairly straightforward fashion using Warp Shuffle. In other words, it may be more efficient to first sum all 32 elements together in the warp using a construct like we depicted on one of the previous slides, one of those Warp Shuffle operations, to sum the 32 values together, and then just have a single thread do the atomic instead of having all 32 threads do their own individual atomic. In so doing, we reduce the pressure on the atomic subsystem, and that may result in the atomics no longer becoming a bottleneck for your code. So that's an example of atomic aggregation, and you might use Warp Shuffle to help achieve that. So we're at the end of the lecture, the slides. In future sessions, we expect to be talking about the use of managed memory, concurrency, analysis-driven optimization, and cooperative groups. Again, a little bit more topical. We're shining our flashlight now into different areas of CUDA programming, not so much on what I would call foundational topics. Again, you might disagree. Maybe after getting through all 9 sessions, you might decide that all 9 are foundational. The homework is structured. Sorry, there's some references for further study. And the homework is structured in a similar fashion to previous homework, so it's available on GitHub. There are allocations or methods that you will use if you're working on Summit versus Cori. In other words, working in Oak Ridge versus NERSC. And as I mentioned at the beginning of this session, we will be staying, I haven't seen too many questions pop up in the chat just yet, but I will be trying to address those, or we will try to address questions real time for the remainder of the time that we have, about the next 30 or 40 minutes. If you have questions about the homework at that point, we will be trying to address those. But the approach that we decided to take, just to repeat what I said at the beginning of this session, is that we would like, because the homework is a little bit more involved and we believe there are some thought-provoking questions in the homework that you may want to have some time to think about before you're quote-unquote given the answers, what we'd like to do is give you that time to think about the homework, to work on the homework, and we have another session coming up. Optional, of course, just like all of these, but if you'd like to join us for that session, we'll do a more ordinary walkthrough of the homework with some discussion in that session. So at this point, I'm going to say we are now open for questions. I don't really see any in the chat. I hope I didn't miss any. But you're welcome, if you have the ability to ask questions online, you're welcome to do that. In other words, voice, or if you want to put them in the chat, I'll try and address those. And I will also invite Robbie to jump in if he has anything he wants to say.
Thank you very much, Bob. Robbie, do you have anything to say as Bob suggested?
No, I think Bob covered it all. I would just say, just reiterate that we're going to have a separate session where we're going to walk through the homeworks, but we wanted to give everyone a chance to try it a little bit first before we go straight into that. So that'll happen next week. Thank you.
So I would like to recommend everyone to stay for the remainder of the session and to join the next one if you're available. From last time, I think the hands-on, just people, you see other people's asking questions, you learn by doing things with experts at your side. It's very helpful. Yeah, the date, there's a question about the date for the session walkthrough. That's next Tuesday. And I'll post that again. It's Tuesday, 3:30 to 4:30 Eastern time, or 12:30 to 1:30 Pacific time. And use the same Zoom session. I'll post that again.
I'm going to, just to make it clear, hopefully, especially if someone watches this recording at a later date, I'm going to go ahead and actually pull up the website where this is posted. So hopefully you can all see my web browser, and I have this tab pointed at the location for the CUDA training series. In fact, I have my web browser pointed at this URL, which is pointing at this particular session. So this particular section is atomics, reductions, and warp shuffle. And if I scroll down on this page, I see that there is a new tab, or an additional tab perhaps.
Tab says exercise
It
walkthrough.
says exercise walkthrough right there. Okay, so previous sessions would have had all these tabs, but this session you see there's a new tab here that says exercise walkthrough. So if you go to this tab and click on it, you'll see that the time and date for the location is given. It's going to be on Zoom, and here's the Zoom link that you'll be able to use to access that meeting at that time. So May 19th is next Tuesday, and so you have about a week, roughly speaking, to do this homework, or to do whatever you want with this homework. And May 19th, Robbie and Max, I'll probably try and join as well as I can, but Robbie and Max I know are teed up to walk through the homework more or less step by step. So at that point, if you have an opportunity to do the homework, bring your questions, and as they're going through the homework, they should be able to answer those questions.
There's a question about Cori GPU access. Yes, normally we give you a week for GPU access from today, and because we have an extra session, we're going to extend it towards the end of next week, next Friday. So you have about 10 days to use Cori GPU. And we have the reservation for today, remaining of the hour, and we'll have a reservation for next Tuesday during the walkthrough. Before everyone, sometimes some people ask, before everyone try to leave, someone wants to leave, I just want to remind people if you can help us with the survey. The survey is also one of the tabs on this page that Bob is showing us. There's a link. And for this event, this page from the NERSC event page as well, this is the registration link. It's also the detailed information link for the Oak Ridge page from the NERSC page. So help us with the survey. Want to know how we're doing. Thank you.
It looks like we have a couple of questions in chat too, Bob, if you want to take a look.
Okay, I'll look right now. Just give me a second. Okay, the first question that I see is, can loop unrolling improve the performance? Generally, yes. I think I may have talked about this in a previous session. I think a similar question came up. Generally speaking, the idea behind loop unrolling is that a loop like a for loop that has a known extent, in other words, the compiler can determine the extent, the compiler will generally automatically unroll that loop for you. And what that means is, in a nutshell, taking each iteration of the loop and laying it out in sequence. So you're getting rid of the loop and you're putting each iteration of the loop in sequence in code. That's really just the first step in optimization. One of the reasons that the compiler wants to do that is that the next step in the optimization very often is instruction reordering. So the compiler will aggressively reorder operations while maintaining the correctness of your code to provide for optimal performance. And I briefly touched on this during the optimization session. One of the things that we want to do with unrolling or optimization generally is try to get all of your memory operations launched right away so that they can get into the queue and you can get your memory subsystem going as quickly as possible. The sooner you get the memory subsystem loaded with requests, the sooner the data comes back and the sooner the results can be calculated. And so if I have a loop that loads from global memory on each iteration of the loop, On the 10th iteration of the loop, if I just followed the loop semantics, on the 10th iteration of the loop, I would load the 10th value. But if the load operations are independent, which they often are, there's no reason I couldn't load it right away. Get that load operation launched right away, and then do the operations that I can do in the order that they can be completed in. And so the first step to be able to make that sort of a code refactoring possible is for the compiler to unroll the loop. Once the loop is unrolled, in other words, eliminated, then the compiler can start moving things around, knowing what the requirements are to be able to move things. And in so doing, we can make our code run a lot faster. So that's the basic idea behind loop unrolling. Normally, it's an optimization that I would leave to the compiler, but if you look in the CUDA programming guide, it turns out there is a pragma that you can specify. So a pragma is like white space in C. It's a directive to the compiler. It's not C or C++ itself. But a pragma is a statement or a directive to the compiler that says, please do something for me if you understand what I'm asking. And there's a particular pragma that's defined for NVCC, in other words, the CUDA compiler, that allows you to specify loop unrolling according to a particular set of parameters, basically the unrolled length. And there may be some situations where you might want to take control of the unrolling process. The last thing I'll say about unrolling is that it's pretty important for the compiler to be able to understand your loop. It's generally desirable for the trip extent, the number of loops that will ultimately be computed, to be known, in other words, discoverable at compile time. So if you can write loops that have a discoverable trip extent, those are more likely to be aggressively unrolled by the compiler. Those might be what we would call completely unrolled, which means there's no longer any loop and everything has been converted to inline instructions. A partially unrolled loop might occur as a result of the fact that the trip extent ultimately cannot be known, but some level of unrolling may still be possible, and a certain level of unrolling allows for a certain level of optimization. But the loop is ultimately still present in the machine code. So if you're really interested in loop unrolling, the best thing that you can do is give the compiler the best possibility to do that, and one of the ways that you can do that is if there's a way that you can make the loop trip extent explicit, in other words, discoverable at compile time. How many warps are available actively for a grid block? So in the previous session, 2 sessions ago, we talked about what a warp is. A warp is a subdivision of a thread block that consists of 32 threads. So if my thread block has 32 threads, by definition it has 1 warp. If it has 64, by definition it has 2 warps, and so on, up to 1024, which would mean that the thread block consists of 32 warps. So first and foremost, the warp is a logical subdivision of threads in a thread block. It also so happens that warps are relevant for execution behavior. Warps generally execute together. An instruction is not issued per thread, it's issued per warp. We don't normally talk about it that way in the CUDA programming model, but nevertheless, that's the actual implementation behavior of CUDA hardware, CUDA GPUs. That's the way they operate. They don't issue an instruction per thread, they issue it per warp, and so we often say that a warp is executing in lockstep. So the question, how many warps are available actively for a grid block? The first answer to that question is how many warps are in the thread block. That's how many warps are available. Remember that when we're talking about execution behavior, a thread block executes entirely within the context of an SM. And an SM, which is a portion of a GPU, a hardware segment of a GPU, has a maximum number of warps that it can support. In many cases, that number is 64. 64 times 32 is 2048. That's equivalent to the maximum complement of threads that an SM can support. So at any given time, an SM can have up to 64 warps active. In other words, it may have a situation where it can select an instruction to issue from any one of 64 threads in a particular clock cycle. Now, whether or not it does that or not is going to be a function of what else is going on in the SM, what execution units are available, and so forth. But potentially, you could have up to 64 active warps in an SM. And I don't see any other questions in the chat. How are the masks for the warp shuffle operations determined? I kind of glossed over that, but the mask is actually a bitwise data structure. It's a set of 32 bits, so it's always an unsigned int quantity in C, or speaking with respect to C or C++. It's an unsigned int quantity, and each bit corresponds to one thread in a warp lane. A warp consists of 32 threads, and so we can imagine that there are 32 warp lanes, one thread per warp lane, numbered from 0 to 31. And likewise, the bits in the mask are numbered from 0 to 31. And so if a mask bit is 1, what it is saying to the execution engine is that this warp must participate for correctness of this shuffle operation. You can have a shuffle operation that's operating with fewer than 32 threads in the warp. That's totally legal. But you need to tell the machine what your intention is. The mask does not have to be a compile time constant, even though I showed it as more or less a compile time constant. It's actually a runtime variable. So you can compute it at runtime. But nevertheless, the value that you compute, the bits that are present in that unsigned in quantity, will indicate to the execution unit that the warps that have, the threads in the warp that have a 1 bit must participate. Now, to go beyond that in terms of explanation, we need to get into some nitty-gritty details of execution behavior. First of all, I've already indicated that conditional code that you write in the C or C++ language can easily be used to select a set of threads. We've already seen how to do that. If thread ID is less than a number, then do this. What that means is, in the body of that if statement, the do this part, only the threads who satisfy the if condition will actually do that, though they're the only participating threads. If I attempted to do a warp shuffle operation, which for correctness required other threads besides the ones that satisfied the if condition to participate, and I issued that warp shuffle in the body of that if statement, that would be broken code. Now, what happens after that if statement? Well, the if statement created something that we call divergence. Some threads are active and some aren't. Some threads are doing something and some aren't within a warp. Okay, normally, we'd like to think of a warp as all threads executing in lockstep. I issue one instruction to one thread, it's the same instruction issued to all threads. However, we already know that conditional code can break that lockstep concept. Within the body of the if statement, we have to be very careful to pay attention to our if semantics to make sure that our mask lines up with our conditional selection. Anything else is broken code. But the question arises, what happens after the if statement, after the body of the if statement, or if else, after the conditional code is completely done, what do I know about warp execution behavior? It used to be that we would declare the warp reconverged at that point. We would assume that now, once again, I'm outside of the body of the if-then-else statement. I would usually assume as a CUDA programmer that my warp is so-called reconverged and all threads are now executing in lockstep. However, for reasons that I don't wish to go into right now, in the Volta programming model, so for Volta architecture and beyond, we chose, from a design standpoint, to allow the GPU more flexibility than that. So we now have a situation where the divergence that was caused by conditional code can persist beyond the conditional area in my code. And there might be some performance reasons why I might want to allow the Volta processor to behave that way. Typically, we don't observe that in Pascal and Prior, but in Volta, it's definitely observable. And even in Pascal and Prior, if we go back to first principles of CUDA, we know that the CUDA programming model does not impose thread execution order. So even in Pascal and Prior, it would have been legal for a warp to persist in a diverged state even if the conditional code did not require it. As long as all threads execute the code, I can have correctness, and it's legal. In practice, Pascal and prior, that didn't happen. It would reconverge at the end of the if construct or at the end of the conditional code. In Volta and beyond, the compiler no longer has a mandate to force reconversion at that point, and if the compiler decides that there's a good performance reason to allow the divergence to persist for some time longer, it's okay to do that. It's legal. It's always been legal. So the question arises, what about the converged state of the warp after the conditional area? Well, this now becomes a gray area. We cannot assume that the warp is converged, even though it seems like it ought to be. If I then run into an instruction which requires convergence for correctness, like a warp shuffle, I now have a big gray area and a question mark. And so the CUDA programming model, or really these intrinsics, were adjusted in CUDA 9 to account for this gray area, and the old intrinsics, which you may still see in code, are deprecated, expected to be no longer used. And the new intrinsics include this mask parameter, and what the mask parameter says, let's say to the compiler, it's really, we could imagine this happening at the execution level, it doesn't matter. But what the mask parameter is saying is, regardless of the convergence state of the warp, if the warp is unconverged, and I'm not in a conditional area that prevents this sort of convergence, you must reconverge the warp to this level so that the operation that I'm about to execute is valid and will complete correctly. And so that's what the mask parameter does. It says, it doesn't really say anything unique or novel in the area of conditional code, because if you've only selected a subset of threads for the warp to use, that's all that's going to be used. You can't adjust that or fix that or correct that or modify that with the mask parameter. But in this gray area where unconverged warps may exist, but it's not obvious because there's no encompassing conditional area, then I want to address correctness, and the way I address correctness is to specify explicitly the threads that I need to participate in the shuffle operation for correctness of my code. It doesn't always have to be all 32 threads. Again, if I only need the first 16 threads, that's all I care about, then I can specify a mask parameter that only indicates 16 out of the 32 threads. Perfectly legal. And the compiler or the execution unit, whichever, will only guarantee that those 16 threads are converged when that instruction is executed, and that should be correct. So that's what the mask parameter is all about. What does 8888 mean as opposed to OXFFFFF? So OXFFFFF, if you look at the bit pattern, means that the 16 threads on one side of the warp are participating, and the 16 threads on the right-hand side where the zeros are not participating. If you look at the bit pattern of 8888 expressed at the byte level, that is, or at the 4-bit level, that is 1000, repeating, 1000, 1000, 1000, 1000. That's what the 888-bit pattern is. And that means that the 3rd thread and the 7th thread and the 11th thread and the 15th thread and the 19th thread must participate for correctness. OXFFFFF says that threads 0 to 15 or 16 to 32 must participate for correctness. 7777 means that all of the threads except 3, 7, 11, 15, and so on must participate for correctness. This is just interpreting bit patterns. That's all that is. There's no magic there. Just realize OXFFFF 0000 in a binary realization instead of a hexadecimal realization. And wherever you see a 1-bit, that thread must participate. Each bit corresponds to a warp lane, a thread in the warp. When you have multiple warps in the thread block, the same pattern is applied to each warp. And generally speaking, the same operation would be executed for each warp, perhaps on different data. there's actually a CUDA blog that goes into this in some detail, and a number of questions on Stack Overflow that pertain to Warp Shuffle and Mask and so forth. So those are a couple other resources. The CUDA blog, I believe, discussed, it was either CUDA 9 or cooperative groups, but it also talked about Warp Shuffle and intrinsics and so forth. So a bit of Googling there will find you additional resources if I didn't include them. We're pretty close to the end of the hour, and I don't see any more questions in the chat. So I think it's probably time to wrap up.
If there are no more questions, let's give Bob a round of applause. You probably can either unmute yourself, or there's a reactions button at the bottom of the Zoom chat. You can push putting the reaction. I don't know if that works. I'm trying that. Oh yeah, see, you got lots of those.
Great, thanks.
Thank you, Bob.
Okay, I'm going to sign off. Thanks, everyone. I appreciate your attention. Hope you're finding this series useful, and I hope to see you, if you're interested, at the homework session next week, Tuesday, and for the subsequent training sessions, which will be approximately monthly.